Well, hello and welcome back to Old School Coding. You know the spiel by now. So, in the last session, I put together a number of ALU instructions and started some testing of it, and then kind of said, well, I'll do it offline because it takes a while to put together test vectors and get tests running and all that. And that's just basically this loop of write some code, run it, think about it, consider what's going on, try to generalize it for other things, loop. So what I ended up with, I've got Get Kraken up here showing the actual commit that I sent up. We modified a whole bunch of tests, but here's the ALU test. We can look at it in the editor shortly. Let me bring my editor, Get Kraken up to the top here. There we go. So basically, just like the 8080 shuffles its tests out to subfiles, I went in for the ALU stuff and I said, well, let's set up a separate function to test each one of these things. And in the process of putting all this together, I realized that these get kind of ugly. And if you're running test A, then test B, then test C, each one feeds initial conditions into the next one. So as of this commit, I hadn't yet worked out how I wanted to fix that. I was still working out what the instruction sequences were going to be and what I wanted to test for equality and so on. And it's not a complete test. For obvious reasons, I'm not going to test that the add actually adds. I'm going to say if it looks like it adds, then I'm going to assume that the add instruction on my host system is working. Did a whole bunch of other things. In the light of trying to speed the later process going, I built where'd it go? I built gen opcodes up a bit, and not much in this one, but gen opcodes is now getting beefed up to do more things, and it will get beefed up in the next few commits after this one. I also brought up a whole bunch of assembly code programs that I would be interested in working with. For instance, I have my Fig4 8080 source code. I found a whole bunch of example CPM. This is actually from the CPM 1.4. Oh, this is actually from the CPM 1.4 manual. And then I had to grab the 2.0 version of it, which was copy pastable, and then go back and edit it to be more like 1.4. So this is kind of a merge. There's various other bits of code from the CPM manuals. CPU diag was something I found on the CompSys CPM newsgroup from 2002. Kudos go out to Kelly Smith from Microcosm Associates, who made it available. This is the validation test that they used to make sure the 8080 chips in their systems were working. So we'll be using that. We have standard stuff from CPM like GetSys and PutSys, which have some areas where perform discrete at this point, for instance. All good stuff. I see a lot of Gary Kildall's hands in that. He was quite the character. Top flight engineer and teacher, mentor, friend of my father's, all around good guy. There's some MDS source code that was also available from the CPM manuals. Believe it or not, I'm learning more about the MDS from the source code for the BIOS in the CPM code than I could find out from MDS documentation. I didn't have the complete BIOS source code in here. I may do that, but all I've got of that is a PDF image of it, so I would have to type that by hand, and it's long. I have extracted some information about CPM here. Our ALU tests, of course, turn out these big figures. I need to turn off the grid on those at some point, and all those get updated. So that was the first commit. It included a whole bunch of testing stuff. I did a follow-up to that where I actually brought in all of the 8080 opcodes. Went over the documentation with a fine-tooth comb to bring out all of the documented instructions and built them up into the Python script that not only provided my macros for me, which are now in a more consistent form, but it also gave me a table which I encoded here in the 8080.org doc file. So this is actually a grid of all of the 8080 instructions. The dashed lines here are opcodes that have no documented behavior. I will be setting up the simulation so that if we encounter one of those opcodes, the simulation will simply stall. I may, in fact, put in something that causes it to stop dead in its tracks so I can get a trace back and look at what's going on and find out why we got to an area of memory with an illegal opcode. Different chips from different manufacturers may do different things with those opcodes. And because of the way these things work, the same chip in two different systems may do different things. For instance, if it is reading from the data bus into a register, and it's latching the value into the register, but it's not also turning on any drivers to the data bus, then what you will get will depend on what that data bus floats to in that system, okay? So these dashed lines, you can't even say that they're going to have consistent behavior from system to system. Some of them may even put the chip in special testing modes. With the old 8080s, this didn't happen because you don't simply do that unless you have a lot more gates available. So we've got all of our opcodes. I realized that we had a 2-byte operations handler. This is for handling the second byte of a multi-byte instruction. And we provided a handler that goes in the last T state of the existing machine cycle. But I can see by looking at the diagrams that we're going to need a way to say, run this as the next T1. So I'm exposing this state 2 bops as part of my 8080.h. The implementation gets all of the new macros. The consistency I was mentioning was that we now have 4 characters wide for the operation, and that means if these opcodes that are only 3 characters wide, there's going to be a couple of underbars before the operand. Okay, some small changes. Never mind that, that was just a goof. I retired tau.c. Tau.c contained just that, so it's now just folded into support. Since the external declarations in support.h, that's not a big change. Our tests, of course, have to use the new opcodes. So that's all that change was. Oh, and I have modified the build script so that the build that I'm doing doesn't echo the commands as it's going to execute them. It just simply completes. The build is fast enough, I don't need progress markers. So that's all just kind of cleanup. Nothing important to look at. And then I expanded the ALU test. So beyond the 4 tests we had, add, subtract, add, carry, sub with borrow, I added tests for and, XOR, or, and compare. And I did not go through and make sure that I tested each instruction with all of the possible flag results and all of that. I just blasted some values in. We'll do a more complete test later. What I wanted to see was some indication that most of this was just kind of basically functional. You see all that added stuff there. And that's where we sit now. This actually took me most of the day yesterday and today. It is late at night. Normally at this point I would be shifting over to streaming some games, but when you have an idea and you're motivated, sometimes you'll dive into this stuff late at night. This may be a shorter session though, so just be warned. So we can dismiss Get Kraken from the screen. Here, it's gone from OBS and from my display. There. And let's get our make command into Emacs. Make-c-k-j. And this is called cycle. Ah. And readme.org will be behind my picture. If you ever want to refer to that, it's literally the front page of the project on GitHub. I just like to keep it there because that reminds me where I'm going and what I'm doing. I think I upgraded README at one point to add things that were missing. Yeah. So there we are. And we're ready to start on some more instructions. So let's turn my PDF viewer on. I figure if I am going to keep editing things in the rightmost panel, then I might as well organize my editor so that the PDF is over on the left, so it's not showing. Because I do mostly like to edit in that rightmost panel there. The other thing I need is bin there. So, what instructions do we want to add? Well, I don't want to get started on dealing with referencing memory through HL quite yet. Nor do I really want to do anything that has 16 bits of immediate data. I'm going to try to fill in some instructions that are just the same kind of pattern we've had. So I'm looking for 1 byte instructions. So nothing with an M2. We could just start going down. It was just miscellaneous instructions. Let's see, SPHL, XCHG, increment register. Let's do increments and decrements tonight. Yes, that looks good. In fact, I am going to run this back down to 1 page. And let's see, I can actually make it a tad bigger. I wonder if I can go to 125 and still show it on the screen. Might be, because that is actually much more readable. Now, I could actually crop the image there so it didn't take up quite so much of OBS, but I don't think that would get me down to showing a lot more of my editor in the background. So we'll just do it like that. And I'll turn the PDF on and off as we need it. So the first thing we're doing increments and decrements. So I'm going to start off with I and R right here. So first step is actually building the source files. So we're going to go into Inc. And nothing goes in here because that's the wrong file. I don't think I'm going to need anything additional for the increment register stuff. If we look at the PDF again, I should have gone over this before I dismissed it. The actions of INR are simple. In T4, we're going to take the destination register, move it into temp, and we are going to take temp plus 1 and put it on the ALU's output. And that's in T4. And then in T5, we are going to latch from the ALU back to the destination register. So we need a T4 and a T5 for each of these. And I believe it's 1-to-1, yep, because I have a separate T4 for each destination register. It'll know about its T5. So we do not need an M1 T5 in this case. So we may fill in M1 T5, but the M1 T4 that we use will not use that in direction. Let's go here. Increment, decrement, we'll do the same thing. It's a minus. This is a incorrect thing, DCR decrements by 1. I think I can use increment INX and DCX as well in the same logic to do register pairs. So the register pairs, what is the actual path that the register pairs take through the CPU block diagram when they do this? And clearly I need to have my PDF viewer a little bit bigger. Some pages are slightly bigger than others. So if we're going to increment a register pair, it goes from here. Instead of going out to the data bus and around to here to temp register, incrementing by 1 into the ALU output and back, instead it goes down to the increment or decrementer down here and then back. So we need an IDAL, which is wide. So let's add that while we're looking at it. Word. Actually, this is the adder because I want to be able to track what's in here. So now that we have the IDAL, we are going to have to start using it. Which means anything that's along this path where we're going to do an address buffer and go out there, it really should be there. So maybe our first step here is to retrofit all the places that we upgrade, where we increment the PC, so that we send the PC out to the IDAL and then to address, and then increment it and send it back to PC. Yeah, let's look at that first before we start adding the instruction. So essentially what we've done is we've identified a functional unit in the 8080 that we now need to model to do the new stuff, and it's involved in old stuff where we kind of waved our hands over it. So typically what we have here is PC out status is in T1. It needs to maintain the address up until the middle of T3, but it needs to write back the incremented PC sometime during T2, which means I believe that the IDAL has a latch, and following the latch it has the incrementer, which provides the data to go back. So let's write that code. Source. This is all in fetch for now. So adder to that, this is actually to IDAL. Oh, and I have a cat who wants some attention desperately. Hold on. Yeah.
She's ready for me to go to bed.
You ready for bed?
I'm gonna go to bed after this episode.
Okay. So the cat doesn't want to come say hi on camera. She wants everybody to go to bed because it's bedtime. She gets kind of insistent too. So where was I? Okay, so we're latching PC into the IDAL. We are sending the IDAL to the address register. And now here where I send it to PC, I want to do adder to CPU. So we're going to actually model this as an incrementer. This may cost us significant performance, and we can come back to this later and get rid of it if we need to. And now that I think of it, the IDAL needs to still have the data that we are latching, because really there's a latch followed by a incrementer which sends things back. The incrementer probably doesn't latch. It probably just is +1 of whatever was there. Now, I didn't look carefully at what our performances were. Let me snapshot this. Oh, wait a minute. Our numbers vary somewhat from run to run. So being able to see how much of a performance loss this is may be difficult. And of course, if we start capturing IDAL, that's going to be yet another source of things happening. So where else do we do this? Well, in I-8080 2 bops, we have the same thing. If C had inheritance, we would have just inherited that across. Notice the differences here. 2 bops T1 is just the same thing, but with a different status and a different output state. 2 bops T2 is just PC Inc. And we're incrementing from the IDAL. Yeah, anytime you are trying to take the output of a latch, operate on it, and send it back to the same latch, you know that there's something going on there in the hardware that's not exactly that. So with that in mind, let us do a git grep of PC. That's behind the PDF, but we'll see it here. Skip over the ASM files and the doc files. Back to there. Okay, so where we're manipulating PC, we also probably need to look at manipulating IDAL. So adder invar of PC. In fact, I'll just put IDAL underneath the PC here. Fix the comments there, and there's probably comments in fetch that are the same. Halt. Halt does not increment the PC, but it should still be using IDAL to send it there. So just to keep us from being too confused on our traces, I set some registers to Z here during reset, whose values coming out of reset may not be well defined and may not be interesting if they are well defined. So IDAL I can set to Z, so when we reset the CPU, we come out of reset and we're graphing things, we're going to have some random value in IDAL. I could actually go through here and simply set everything high impedance right off the get-go, everything that isn't guaranteed by reset. And now that that thought has occurred to me, let's do it. So things that could be high impedance, or the Z state. So Z is going to be my reset weird state thing. What are the chances that I am going to want to do a push button reset diving into a debugger? Actually pretty good, so I don't want to do that to any architectural state, but let's check the internal states here. So I've got PC, IDAL is down here, address bus, data bus, IR, ACT, and TMP, and ALU. We're going to Z those out so that they aren't in our face. And flags. We don't know what the flags are. This means that if somebody does a conditional branch of some sort on the flags after a reset, we don't know whether they'll take it or not. And when they do take it, we'll not be able to see what's in the flag byte when they do. But I believe data Z puts an FF in there, which is not a valid value for flags anyway, so we're good. Let's see, I think those are our only, yeah, those are the only things that can have a Z state. Okay, so back to our scan. So coming out of reset, we shove a 0 in PC, looking for things that deal with IDAL specifically. So these expressions could use the CPU, which is here. Let's just, apparently I did this a number of times in this file, and that was the last one. CPU is TS CPU, so TS drives PC via IDAL. This is the C. Oh, so now she wants to be picked up. It's my little Nate Light co-pilot. Increments. How am I going to edit this with a cat on my lap? So I realized a long time ago that no matter how long I lived, I would never get to the end of my life and say, gosh, I spent too much time holding cats. That will never happen. So while I'm sitting back and thinking, we've got this incrementer, decrementer address latch, and I believe I've hit most of the cases that are important for it. Yeah, there's only a few more. I do need to update that comment. And now she's twitching. You ready to get down? You ready to get down? Okay. She doesn't get to jump down anymore. She's getting old. If she can't jump up, she shouldn't be jumping down. That's my thumb rule. So increments IDAL into PC. And again, TS arrow CPU becomes CPU. Probably in a number of places in this test. Nope. So as part of my test reorganizations, when I was writing the 8080 tests, I realized that there were many subtests, and each one wanted to have a well-defined starting state. So now I have these guys here. No, it's not these guys here, but I now have well-defined bits of code. Test I8080. I believe that's in the other file. Let's get to that. So before we run each one of our tests, we have this reset for testing thing. So I'll do reset post to make sure reset is working. And then I will go through a special reset cycle, which is very abbreviated, whose primary purpose is just to form a consistent starting state for the rest of the tests. I'll do that between them. And we do the same thing for BIST. So once we've tested reset, we can say reset for testing, test MVI, reset for testing, test MOV, reset for testing, test ALU, reset for testing, test EIDI halt. Now, if we're in the halt state and we reset for testing, it will come out of the halt state. So in fact, I can go back to testing halt right there at the beginning. Because now I know when I reset to do the next guy, it will get us out of that. And what we're doing there is an abbreviated test where we do a clock to make sure that we aren't in the same cycle that something else happened. We force the ready input and the reset inputs to be in the reset button is pressed state. And we run it until we see phi 2 going high and then low again, so we know we're near the end of a T state. One more clock. And then we set reset and ready to their inactive states. I'm actually not spending the extra time. Let's do one more. Let's move reset first. So what I'm going to do is I will go to just before the beginning of the cycle, then I'll hit reset. And I'm going to do this twice more. Give reset a bit of time to move. And actually, I believe reset, by definition, has to be there for 3 cycles. So let's split the difference. There. So the documentation for the 8080 says that when you assert reset, it should remain asserted for 3 cycles to allow internal state to go. And this will get us at least that long. So just in case there's something in the way that the 8080 is designed that forces that, this will take care of it. I'm going to bring us out of reset, and I'm going to give us, oh, hold on. if I change this, it's going to change where we end up because I'm going to run more cycles afterwards. So let's get diff i8080 test.c. Yeah, I thought so. I shouldn't be doing this. I should not be changing this guy. So we're running an abbreviated reset cycle. We're pulling reset, and we're running until we see phi2 go high and then low again. One more cycle. We're releasing reset and ready, and we're waiting for reset to go high. This is the synchronized reset, which will go high later in the cycle. And then after the synchronized high reset goes high, we're waiting for phi to come back down to 0. And then we run to tau plus 11, and that's the value that I found that left us ready to execute the first oscillator uptick of the first T1 of the first machine cycle at 0. So this leaves us ready to start fetching the instruction at 0. And now I see that the only change I've got made to test.c to 8080 test is I moved around the EIDI halt stuff. So now if we go back to our normal build, we see that we are running correctly, and all of our PC increments are now being routed out through the incrementer or decrementer address latch. I am going to call that a delta, and I'm going to jam that right in through Git Kraken. And I'm not sure why Windows is telling me that my Windows in copy mode. Kind of like Git Kraken. Summary, add ID incrementer. Okay, so there's the comment for that block. Our net changes are add IDAL, initialize it, set its name, set up 2 bops to use it in EIDI halt, use it in fetch, update it in reset, along with the other registers. LU test, I had some renaming, so I didn't need to use TSR CPU, I could just use CPU. EIDI halt, same thing. Fetch test gets comment changes. Same. This guy gets the EIDI halt moved around. Stage all changes, commit changes. There we go. And back to our coding, and now we have the incrementer decrementer address register handy. So if we go back to our PDF, we now have the correct paths to do the increment INX and DCX. Remember, it's increment or decrement, so we use it for increment and decrement. DAA would fit inside this set of things we're doing, but it's not really increment or decrement. Let's see, just increments and decrements, and then if we have time, we will move onward to other single byte instructions. Next page of the PDF. What other single byte instructions do we have? Complement accumulator, CMC. These could be wrapped up tonight, but they're not part of increment and decrement. There's a whole bunch of stack operations, which we are not going to start on tonight. Yeah, let's do increments and decrements, and then we may sweep up the rest of the 1 byte operations if we have time tonight. PDF off. Okay, so back to our implementation. So increment decrement is going to look kind of like EID halt, and it's going to be a collection of instructions, right? So what I'm going to do is I8080 incdec.c. And we are not going to copy the whole thing at once. I'm just going to bring over individual lines as I need them. Comment I8080 incdec. To write later. Okay, so what do we want to do for increments and decrements? Well, let's start off with the first increment decrement. PDF on. We're looking at increment registers. We have those for the 7 8-bit registers here. So we're going to need a macro that does this bit for each DDD and a macro that does that bit for each DDD. And the best place to get that macro or something like it would be from MOV. So these are not MOV, these are IncDec. Actually, we're going to need increments and decrements. Yeah, let's do them as separate macros. That's not right. So the increment T4 will look like this. Duplicate that, change T4 to T5, and they look like that. Duplicate all that and change inc. Actually, inc becomes INR because I want to say increment register. And the actual instruction name is INR, yes. And this inc becomes DCR. Just like that. Now we need to instantiate them. Lots and 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 lots. Let's just copy this. I'm just going to put it right there. fact, let's do this whole thing. So interesting thing is that one of the common editing, I won't say macros, editing tasks that are they're just quick to blat out is put up a little bit of code like I would put up just this, duplicate it and change something. Take these and then build these guys out. Take this whole thing, duplicate it and change something. Take this whole thing, duplicate. Each one of those duplicate and change something doubles the size of your code. I did this with a byte copy routine for the Spark at one point, trying to take into account optimizing it for relative cache line residency. And I achieved some interesting performance boosts, but I wound up with over 65,000 lines of source code. That's with multiple assembly code instructions per line. So take that with a big grain of salt. It's an effective technique, but it can certainly chew up your source code size. And yeah, that change, I presented it with a caveat that I didn't expect it to be accepted, and I got back the word that, yeah, we're not going to do that. Even though it gave me like a 5% increase in the speed of vcopy, which translated it to like a 2% increase in the speed of the operating system. But it was so much text that it blew your instruction cache if you were doing anything but benchmarking bcopy. So, yeah. So this should give us increment register and decrement register M1 and T5 and M1 T4 and M1 T5 code. And now we need to implement. So let's grab this macro. I'm going to keep this comment on them all because all of these have this same really weird thing where I'm repeating the definition of the function after, declaration of the function after its definition just to soak up that trailing semicolon. Change underscore M1 to underscore INR M1. Okay. Now for the INR M1 cycle, M1 T4, we need to put the destination register into temp and add one to temp and put it in ALU. Data to temp from CPU R value, well, that's already there. Now, one could argue that it's not determinate whether the +1 should go in T4 or T5. However, the 8080 chart that I've got here says it happens during T4. So that's where I'm going to do it. And I am not going to dive into this table for the next instruction. I am instead going to say this is name INR M1T5. Just like that. So now we have a whole bunch of warnings, which are hidden by the PDF. We don't need to really look at them yet. All these functions that we've now implemented down here, 8080 state INR T5B is used but never defined, yada yada. Okay. Okay, so now the T5 state. Now this one, we're not using a state next. This is our final state. So we will be grabbing this ret M1 int which says that after this M1T5, we will be going back to doing an M1T1 cycle. And this is going to say, take the value of the ALU, jam it in the register, and we're done. Now, actually, it's quite possible that we have many different places where the ALU goes into the destination register. Let's take a look at the thingy here, and what I see is increment register, decrement register. MOV uses temp rather than ALU. Looking at the big long list of instructions here, I don't see any compelling reason to share these implementation functions with another instruction. In fact, INR and DCR are going to have the same one. We will share that. So instead of INR M1T5, we're going to have something in common. Call it ALU to R. So ALU to R will be a final T state that writes the value back into the ALU, and it will be available for use inside the Inc deck area. I don't see any real need to share those out to other instructions. I didn't see any other instructions that really needed them, but we'll do that. So now we take the INR macro here, change that to DCR, and the only difference is that DCR decrements the register. So I've got all these functions. Build DCR M1T4. Okay, defined but not used means I just haven't hooked them up yet. And the easy way to do that is to form these arrays. I'm just going to stick them in here. Okay. So now, if we turn off the PDF, we can see we are down to the warnings that the two tables are not used, and that's it. So now we need a loop like what's in the table here for int ddd equals 0, ddd less than 8 plus ddd. So this is state INR T4. If we have one, we're going to do stuff. Now the increment register opcode, INR is hex 04 plus the DDD left shifted by 3. We're we're going to do the same thing. And the DCR opcode is 5. In fact, let's do this the same way we did it above. As a guard clause, so we don't have to worry about the fact that we're defining the same variables twice. How about that? Compiles, and I didn't break any of the tests. Well, did we actually call this? Now I want to move EIDI halt back up to the top. We defined these first, so I'm going to do them first. I moved MOV down because I can't test MOV without MVI. So this is now a better ordering. So the other thing I need to do here is add in the InkDeck testing. Where's BIST? There's BIST. Wherever we have ALU, we're going to add InkDeck. And of course, we haven't declared those yet. I was awfully consistent about EIDI halt being at the bottom, wasn't I? Too bad I didn't think of, well, it needs to be below reset. Okay, so implicit declaration of InkDeck BIST. Init post BIST. Okay, so now I need to implement them. I put the implementation in the test directory, didn't I? Okay, so now the tests. This is actually going to look more like the ALU test. Okay, so we'll do a inkjet bist INR inkjet bist DCR. We won't worry about post quite yet. Get the bist working first. So, downside is we're not going to get a reset of the CPU between the increment register and the decrement register tests. But we didn't do that over here either. To do that, I would have had to export that reset routine, which makes it global, which means it's visible outside the 8080 area. Oh, that to-do is done. Undefined reference to mauve bist. What? Oh no. Have to be careful what buffer I'm in when I do those edits. Okay, multiple definition of mauve post, because it's over here. There. Notice no benchmarking yet? Yeah. When it comes to CPU stuff, we'll handle our benchmarking differently. So the typical pattern I've been following for these subtests is a prologue looks something like this, where I can have a little test program on the stack, copy it into memory, wherever the PC is, and start it running. And this depends on the PC pointing at the next instruction we are going to fetch, and it's not being in the middle of whatever when this happens. So yeah, it'd be really nice if we could reset between them, so I'm going to do that. i8080 reset for testing is now no longer a static function. We are going to move that up above the first static function. So at this point, this guy actually has all of the test context available from here. It's not actually calling into TS, but I could use TS. Yeah, let's just do that. Let's do it right. Which means I do not want to be using these globals. I think most of these are just right there. Are we good? This is no longer static. It's defined in the header. Okay, passing argument 1 from incompatible pointer types. So TS is a CPU test sys here. There we go. This needs to be a CPU test sys TS. Now TS does not actually contain phi. Well, let's chase down who does own it. It's in CPU. It's global. It's owned by Gen. That's right. Only these guys are owned by the environment. The rest of them are all internal. So reset for testing. We want to get this from the person that owns it. So phi 1 and phi 2 are going to come from, actually just phi 2. So we're going to say I8080 CPU equal TS CPU. And P. No, let's get phi from the generator. And edge phi 2 equal to gen phi 2. And reset. Who owns reset? Reset is owned by Jen, I believe. There we go. So now we have a global reset for testing. Which we can now call in between each of the subtests. And we know a reset before we're coming in here, but I'm going to do that anyway, just so all of these are the same thing. Yeah, if I trigger my compilation window to run while the build is still happening in the background, it's going to do weird things. I didn't set up any locking in the build to prevent that from doing the wrong thing in the wrong order. Ah, come on. 8080 ALU test.c. Grab that bit. 80 ink deck. Okay, so now we know that when we enter these guys, we are ready to start the T-state that's going to fetch the instruction at 0. Yay! That's an awful lot of work going around the horn like that. So here's the typical startup that I would get. So we want to do INRs. I'm still going to start with these values. I do want one of them to start at FF, so we get a carry. I want one of them to start at 0.8, so we get a half carry. This will be carry and 0, half carry. I want something to increment to be negative. I'll do 7F here, so increment to H0 and be negative. So I'll do 7F there, and I'll do BF there. So these guys end in F. They're all going to have auxiliary carries set as well. Boom. And there's the INRs. Now, INR takes up 5 cycles, which is the same as the MOV instruction. So our test timing is going to be very similar. We do start with a NOP. In fact, I am just going to grab this whole test function because it's the same number of instructions and everything. We've got the same move immediate. All the assert values are going to be wrong. We'll fill those in with a trust on first run, followed by going over it very carefully by eye. And these adds, add becomes consistently INR. And in reality, these need to be, yeah, there we go. The other thing is that once we do a MOV of this, we're going to do an increment register. We need to test the value that's in the register that we incremented, not the A register. So now we go search for / space INR underscore. That's going to be register name, and we're going to say assert EQ integer right there. The flags, I'm going to set all of these comparison values to FF because we don't know what they're going to be. Actually, let's set them to 5.5 because we know that's not going to be valid for any of them. And that would be a figure that it's I-8080 ALU INR. So that fails that test condition right off. And we only print one failure and terminate, so we are going to go into source support.c, and where we have a fail, I'm going to comment out the abort so we can get all of our failures at once. So the macro for putting something in here is start keyboard macro, search for 0x, delete 2 characters. Switch windows, search for observed value colon, grab that word, and over here we insert format %02x, that value like that. So that now passes. But before I can say the test is passing, I need to check this by eye. Now, you'll notice that all the flag values were set to FF, which means remember we set our flags to the high impedance state when we come out of reset, which means our flags have no defined value. Let's take a look at what the documentation says about INR affecting the flags. INR. All condition flags except CY are affected. So CY is not changed, but all the other flags are. And if we look at DCR, all condition flags except carry are affected. So this is something I didn't remember about the 8080 is that if you increment a register and it wraps around, it's not going to get you a carry. Now, it does get you 0, but you can't do, for instance, an INR followed by a ADC. If you want to add up a whole bunch of bytes, you have to use basically a add immediate. So all flags except CY, which means we need to implement that logic. PDF goes away. So we go back to source I-8080 inkdeck.c. And the ALU flags are set when the ALU changes. Let's go back to source I-8080 ALU.c. And we have this ALU flags thing, which I'm going to copy wholesale over here and change the name of. Ink deck flags. We're going to say unsigned. Well, CY is not ALU right shifted by 8. It is, in fact, the old flag words, amper flags, CY. So calling in, we need to have the auxiliary carry and the old value handed to us. I need to be able to edit this neatly. So temp is that. Okay, so there's our logic. So we grab the old files, we move the value into the temp register, which we will then send out. We grab the temp -1. What are the chances that the subscriber's temp, well, no, subscriber to temp can't reach back and change temp? That would be a hazard which would halt the system. So this is valid. We compute the ALU. We compute the IncDec flags. Unsigned AC is equal to 16 ampere ALU ampere 15 -1. This is not compiling, of course, because of this. If I do this, that should at least get me past any syntax errors. So there's the problem that we can't just define variables inside this without braces. And there's two dodges to get around this in C. One of them is to put braces around the case, which I always thought looked really ugly. And then there's the other one, which is to revert to K&R style, where we do that. The downside of this is, of course, that the scope of these internals are now the whole function. So CPU IncDec flags is not being declared yet. Okay, that's inside my function. That's because it's R defined as B. Okay, so we're good to go. Reindent. There we go. Big block macro. Impl DCR M1T4 does all of these things. God knows why switch was indented like that. So basically we grab our inputs and form our results. We stash our results after recomputing the flags properly. And then we need to do the same thing with increment. This changes the -1 to +1. Notice we do have to do the operation twice in order to get the auxiliary carry. So now all these test conditions that were saying the flags need to be 255 are now failing because they're not getting real values. So now we insert the observed results again. Okay, so now I need to update these comments on the right at which flags are set and consider if the results are as expected. So the inc, is it target.h? Yes, it is. So remove those. Okay, so OX07 is going to be the P flag. O2 is always set, and it can be CY. So 8 incrementing to 9 gives us parity, and the carry flag is still set from before. So what I want to do is do something to clear the carry. So sub AA to clear the carry. Actually, let's do a compare A. And test the value. So this says here, after I have done a compare A, five-cycle long compare A, this is saying that my observed value is 255. That's just wrong. Op compare A, so move I A something. Op compare A should give us a 4-6. So apparently that first instruction isn't doing what I wanted it to do. Let's plot early. Move I and RA. I'm going to plot at that exact point. And LU, let's wipe out all of those. Get a fresh run, make sure we get fresh PNGs. LU INR. This says that our first instruction at 0 was not a NOP. Well, that's because I was copying it into PC value, which may not be 0. Hold on. Stub is percent OX percent O4X. That would explain a lot. Nope, it's 0. We're copying test prog into that value. ROM 0. BF. Oh, BF is the compare A. Her to her. So flags is not being written with 4.6 until out here. Oh, right. Remember the 3 next T2 stuff? Yeah. Need to bump this up by 2, so 9 times 7. This is starting with T3. There we go. So the first thing here is we are seeing a 0x70. Well, let's see here. Do we still have that macro set? Nope. Get these expected values set back to the observed values again. Too many decimal points in number. Thank you. Okay, so back to decoding the flags and checking the correctness. So 4.6 is Z. Makes sense because I am clearing by doing a compare A. Well, not clearing, I'm clearing the flags by doing a compare A. So A is equal to A, and 6 is P, which means the result had an even number of bits set. So ZP, this is the value, this is the flags we see when an operation has a 0 result out of the accumulator. Okay, so we are setting 8 into the accumulator, and that is correct. We increment it to 9, and 0.6 is P. So 9 has 2 bits set, that's correct. So 1, 2, 8, 7F, BF, FF. Just check those by 1, 2, 8, 7F, BF, FF. Those are correct. Incremented values 1 to 2, 2 to, this should be 3, INRC is not writing C back. Move IA8, increment. Move B1, increment B. Move C2, increment C. Move D8, increment D. Move E7F, increment E. H, increment H. L, increment L. Got it. Oh, and what I am seeing here, I'm seeing initial values being written properly. 1, 2, 8, 7F, BF, FF. No. Okay. I think I just have the phasing wrong on, I think I've just got the timing wrong on these. So I see 8 to 9, 1 to 2, 2 to 3, 4, 8, 9. So these are the initial values coming in. Let's set my registers to indeterminate values before we cycle 1. So we don't have any leading values on the plot. Okay, so this says B is not looking good. So write an 8, increment to 9. Write a 1, increment to 2, 2, increment to 3, 8 increments to 9, 7F goes to 8, 0, BF goes to C0, FF goes to 0, 0, and we are not executing long enough to see the whole thing. And the compare A, of course, is doing nothing we like. So what I'm going to do is op MVI A OX 55, and then we're going to do an op XOR the accumulator with itself. And now we need to get the timing right. So move immediate is going to take 5 cycles for the instruction and 4 for this, for a total of 9 t-states. In the end, A needs to be 55. T1, we're going to do it op XRAA. And checking the timing diagram really quick. This needs to be a 4 t-states for the M1, 5 t-states for the M1 because I've got a ROM thing involved. 5 plus, it needs 2 more states into M2 to get the data written. And we should end up with our flags being 0. This really starts with a TW, not a T3. We'll call it after T2. This is 3 plus the immediate, which is going to be another 5 cycles, I think. And let's move our plot up to that point. Okay, so this plot is now stopped right here. So we should see at 0, we've got our 3E, which is move A 55. And indeed, we eventually get our 55 in the accumulator here. Address 2 is XRAA. Boom, boom. So we move 55 and 55 in. And here we get the 0 in the accumulator. I'm not sure I've got the timing right on that. Yeah, I actually don't have the timing right on this one. Hold on. Okay, we should be at the end of T2. So this is the T1 cycle. Okay, so T1 started here. T2 started here. We are at the end of T2. Good. So T3, TW and T3, MVIA and T4. Watching the timing diagram very carefully here. I believe that's 4 cycles on that. So if I put up the M1 return signal on here, that would tell me if I'm in my last thing. So let's go back to I-8080 test. I don't even look at it here. ret M1 int is the one I want to be plotting. There's our signal. So where do I want to plot it? Let's plot it above sync. And I blew the macro already. I forgot to step down by one line when we were done. So I would do this over and over. So there's ret M1 internal. So now we have this nice signal that's telling us this is the last T state. That helps. So now we are going to compare A. Oops. No. That's what was wrong. We're no longer comparing A. Move I 55. This is a XOR A. And we need to run that out through the next T2. There's just T1. So ret M1, there's the T1 cycle to here, and there's the T2 cycle. And during T2, ready is going low because we're going to get a T wait, but during this time, we should now have flags valid. And flags is seeing 6. Which is not 0. That's because I didn't do this right. MVI A55 XRA. MVI A08. INRA. Yeah, I lost track of what instructions were where. So now our first failure is down here, which is off the end of the plot. The plot ends after the INRA through the next T2. So A was loaded with 8. We incremented it to 9. It got written back here. So it's getting written back okay, INR writes it back early. That's right. So INR is going to write it back during that last cycle. So we do not need to go through the next T2 for the increment register stuff. But it is 6 cycles. Okay, so what I want to be able to do is look, you set up the sig plot to trigger after the last t state and be able to see that 9 right there. We do increment from 8 to 9, and the flags have the value 0, 6. And 0, 6 is P flag. That's correct, because no other flag should be set. We're not negative, we're not 0. We didn't get a carry through the out of the low nibble. We don't have a carry, and our parity is 1. So now this is MVIB starting with the first clock. In fact, I can remove these tests because I know that these are correct. And because I have tested MVI prior, I can dust that. Okay, next step is we move immediate into B, 0, 0, 1, and we're not giving it long enough. If I step it down to there, so we know that move immediate B is working, we just are not getting the right value yet here. Because move immediate is going to take 5 cycles for the first state, and then it's going to take more cycles for the next one. So let's start it here. So this will start at the beginning of this instruction. I want to count cycles. There's the first T state. 1, 2, 3, 4, 5. Okay, and that gets us out to here. So this guy is 5 T states long. Then we have this guy, which is 4 T states long. Then INRB is going to be 6 T states plus 2 more for that guy. So this is the move immediate B, 1, increment B. So 6 and 7, there's a move immediate in our operand. This gets into the B register here. We then get our INRB, which writes the data back here. And we are up to, here's red M1 falling, plus 2 cycles. Which we didn't need because INRB does not have to wait. So all of these things where we have to start after T2 only apply to this XRA. So I'm going to put a NOP after the XRA. And then we test to make sure our flag is proper. And this was what, 4-6? And again, let me make sure we are plotting what we think we are plotting. Oh, make sure we're plotting just that much. It's a very iterative process when you want to make sure each little teeny step is doing exactly the thing you expect. So this should be move immediate A, 55, XRA A, NOP. So there's our move immediate. There's our XRA A, and there's our NOP. Boom, boom, boom. Last, and we're done. And that gets our good starting state. So now I'm going to, starting from that starting state, we are going to just do the increment A from 8 to 9. Boom, boom, 2 instructions, and we're properly aligned. The rest of these are just like A. So I'm going to copy paste. Except the B value starts at 1, so it's going to be OX2. And the flags are 2. That makes sense because the P flag shouldn't be set. Okay, let's put in a bunch more. C, D, E. Okay, so C will increment from 2 to 3. D increments from 8 to 9. E increments from 8 to 9. D increments from oops, E, 7F to 8O. And the flags are going to be wrong. So this flag came up with 6P. That's correct because we are even number of bits set. This guy is 6. That is also correct. And this guy is 130, which is 82. 82 is S, and that's it. So I don't have any values here. Well, the D should have, this should have set the aux carry here. No, because I wanted to go from F. Oh, wait a minute. 7F to 82 to 80 should have set my auxiliary carry. So LU ampere 15 plus 1, ampere 16 gives me the aux carry flag. AC is in that bit. So I call ink deck flags with that bit. And AC is being passed in. LU AC old. Let's look at just this guy. So the E register went 7F to 80. That looks like it should be hitting the aux carry. The flags went from 06 to 82, and that's not setting aux carry. Oh, because this is the incremented value. Found a bug. Fixed a bug. There we go. This is why we test. And that changed the result of this condition. So the flags are now 146. Which is 92. This is why I don't simply accept my test results as proper on the first run and say, oh, yes, trust on first use, trust on first result. And then later, when things go wrong, then you have to say, oh, there's a bug. Okay, so I need to fix it in the code and I need to update the test. Well, if you check your values as you're building it and get the test right, you don't have to go debug it later on. Let's do H and L next. Now H and L get the values BF and FF. So BF becomes C0 and F becomes 0, 0. And we very much do not want to see a carry on this last one. So what we're actually seeing in the flags here, we are seeing 150, which is 96. 96 is S, AC, and P. So it's just the same as this. So we got an auxiliary carry and sign, but this time we have the parity bit. And 92 is back to SAC, which is correct. We have an auxiliary carry because the increment passed the middle. We have a sign bit, which is not supposed to be on. Oh, how about if I fix this first? The observed value is 22 decimal. 1/6. So 1/6 is AC and P. So we're no longer negative. Auxiliary carry is set because we carried through from this F to the 0. And parity is turned on because there are an even number of bits set in 0. So that is correct. Let's run this all the way back to the actual test. So there's our increment test. Okay. And Emacs scaled the graphic down because the buffer was too short. Make it longer, I can see it a little better. And all this is correct. So now we need to do the same thing for deck. So now I'm going to flip the values. So instead of incrementing from 8 to 9, I'm going to decrement from 9 to 8. Except we're not. We're going to decrement from these values to whatever. This difference is I'm going to decrement from 8, 0, and from C, 0, and from 0, 0. And now we need to do the same thing as before. Get our test results, copy them in, and then verify them. Start keyboard macro, search for 0x, kill 2 characters. Other window, search for observed value, colon, mark, capture word, come back here, insert, format. Okay, that runs. And now we need to consider if this is correct. So we're using the same immediate values for many of them. 8, 0, C, 0, 0, 0. So 02 is no flags set. Well, that's because we decremented from 8 to 7. Cool. Oh, we need decrement from... Oh, we'll get plenty of half carries later on. Immediate 2, decrement from 2 to 1. We have no flags set. 4-6 is ZP, which is correct for decrement to 0. 8 to 7 again. 8-0 to 7F, which is AC. That's correct. 9-2 is AC and S. And that's S, AC, and P. So that's all correct. I believe that this is valid, and we have now tested the increment register and decrement register. And that took me over 2 hours to put in 16 instructions with all of the built-in self-testing. But we did, as a result, get something that's tested. So the DCR plot looks like that. Eight seven 1 0 2 1 8 7 8 7 F C F F. Okay. Yep. Now this is actually a lot more data than I would normally have with a logic analyzer, because I can just arbitrarily pull signals out from inside the CPU here. And I am beginning to push how much data I want. I want my plots to be that width, okay? Like that, boom. From side to side here, so that they fit nicely on a single page. But that does mean that if I'm getting this busy, these guys, I literally have more oscillator cycles in this plot than I have pixels horizontally. Now, if I had SVG support compiled into everything, and I don't, I could have rendered this in SVG and scaled it up and down and so on, and we would have ended up maybe with small print in the address line and the data lines, but yeah. Notice IR here is now giving us a nice trace of what instruction codes we were executing. 6.5 ED. Some of them longer than others. Memar, you can see Memar going low to read the opcodes and the things. It's not quite evenly spaced because some of our machine cycles are 6 T-states and some are 5. See the blip in the middle from the way that I have implemented the control over the wait states. That looks good. The other ones I want to do, inks and DCX, are a little bit shorter, so we'll go ahead and do those. So INX increments a register pair, BC, DE, HL, or stack pointer. So these are going to be a little more complicated in their logic because I have to take two 8-bit registers, stack them together, do the math, break them apart, and store them. Now I think I am going to have to duplicate all of those, change INR to INX, change DCR to DCX, and ALU to R becomes ALU, becomes IDAL to RP. So what we're going to do is INX and DCX are going to set things up properly. And it's, this is going to have to use the M1T5 stuff because IDAL latches the original value and returns the +1. So the increment actually happens on the outbound side. Okay. So we're going to flip these. INRX becomes INX DCX M1T4. This is actually RP underscore IDAL. So this will be a T4 cycle. It just puts that register pair into the IDAL. Hold on. RP. There, make it a little bit more readable. And then this becomes change from RP IDAL T4 to IDAL Inc. RP T5. Okay, I messed up the names. Actually, just call this INX T5. So we've got this descriptive name here for generic T4 states that are going to toss a register pair into the IDAL. Okay. Then we've got the very specific ones here, which say this is the INX implementation that happens in T5. And these guys are defined and never used. That's okay. Let's grab this whole thing and we copy it to the bottom. So that we can start messing with it. So we are going to need implementation setup for this. How much of this stuff do we want to mess with? IMPL, RP, IDAL, T4 of RP. Yes, static void name INR M. Oops. Name RP IDAL T4 RP. Actually, let's write this out as if it were the final version of this. So RPIDAL is switch. So sometime during T4, we need to put the register pair into IDAL, and that's really it. And the other half is setting this guy. CPU arrow state next is equal to, but there's going to be two different functions that do this, so we're going to go back to CPU arrow M1 T5 of CPU arrow IR value. But we don't have a CPU BC value, so what we have is unsigned B is equal to CPU B value. Oh no. This needs to be RHRL. All these RPs need to be HL. I am so going to have to clear this up. Haha. SP is going to have a different implementation. No, we can actually make do. Hold on. These guys at the top, we can still do these in terms of register pairs. It's just the implementation that's going to be. So we'll do this as RHRL. And SP we're just going to do on its own. Now, interesting question. Can we say name RP IDAL T4 of RH token paste RL? I believe that's a big no-no, because token pasting should be only within the macro itself. So if I don't cast word to RH to a word, there's a decent chance that the compiler will take this 8-bit value left shifted by 8, giving us 0, and concatenate that with RL. So we have to do this right. In fact, let's eliminate RP completely. And I think that should work. I can go back to this. Okay, so IDAL is a struct S adder, so I need an adder too. Silly me. And here as well. And we have no member called SP. We don't have an SP. Interesting. So we duplicate all the SP lines. Duplicate all the PC lines and make them SP. Where it's appropriate. Okay. Got the macro done just in time for the last one. Okay, so this was stuff I copied down that I was going to use as a guide to modifications. Don't need. This says defined but never used, or used but never defined. Right, because we put them in these tables. So now we need implementations for these guys. So something like this. And there's going to be, again, a special one for stack pointer because it's not bytes. Do this one first. INXT5. So during this phase, what we're going to do is we're going to peel the value out of IDAL, add 1, and put it in SP. And because it's all words, we're good. And we are at the end of the thing, so we're going to use, and where to go? There it is, this guy. So there's the increment for the SP. Do the same thing, but for BC to get a feel for the macro. No. No, 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 no. So it's going to be RP is equal to this. Now, I don't have to actually mask this down to the low 8 bits. That happens automatically. So now if we're going to do this based on RH and RL, this becomes name INX T5 RH pasted with RL. Like that. Word. Edge high there. Grab the value, increment it, store high, store low, and we're done. And I am storing data bytes, not address words. And this is an adder 2 down here because SP is an address-like thing. And this is where I have to put in the extra decal INX T5 of RH, RL. Or I get these warnings. Okay, same thing, but DCX instead of INX. Change +1 to -1 in 2 places. There we go. We're not actually testing those instructions yet, but they're implemented. And the 3 tables exist, and they're not being used. So let's set them up. Now in this case, we don't have any that are null. This is INX T4. Actually, this is state RP IDIL T4 of RP. And the T5 is state INX T5 of RP. The opcode is INX, which is referring to the PDF 0x03 with RP times 16. Now, did I remember to set the next state? Yes, I did. So we're using M1T5 here. Now this is DCX. DCX is hex 0B. Big long pause at the beginning is because it is running a big, huge Python script to convert each of the traces to a file. It's huge because it imports something really big, and I call it up for each plot individually. Silly of me. So I unfortunately don't have LXI implemented, so I can't load 16-bit literals into a 16-bit register right off the top. Next question is, what flags are modified by INX and DCX? Let's turn on the PDF and go find that, because I am not doing anything with the flags. Okay, INX and DCX, no condition flags are affected at all. So that is correct. So we are going to set the flags to Z, and I'm going to assert that they are Z throughout the rest of the test, because nothing I do should change them. Just a second. Empty soda. Okay, not a full mug of soda, just enough to wet my whistle. So, BIST INR gets modified into BIST INX, and DCR becomes DCX. Now, just that mechanical change is not going to compile, of course. If it did compile, it wouldn't be correct, of course. So, what we need to do, first of all, A doesn't matter. B, C, D, E, H, L. I don't have any way of setting my stack pointer. Oops. Okay. What do I want to do in a way to set the stack pointer? I will have to set it manually from the simulation by manipulating the state of the register because I don't have instructions to do it yet. So we'll do that right off the top. And what I'm going to do is I'm going to increment the register pairs twice. So what I want to do is make sure that I can see both registers do something. So what I want to do is, for instance, BC, if the B is the high part, I'll do something like that. Now, SP, don't need to worry about A. So I do want to be able to see increments in the upper half of the register, and I want to increment twice so I can see the lower half go from 0 to 1 as well. Or, well, let's see, if I set this to 0x, AA 7E, so I can increment 7E to 7F, then 7F to FE to FF, and then FF to 0, 0, increment the AA to AB. Let's use that pattern. So what this is intended to do is catch possibly B and C being swapped when I do the increment, or one of them not being written. So we do get updates to them both. Take a look at this. I believe this is a 5 T-state instruction with 1 wait state. Gives us 6 total. Bringing up the plot really quick. So I and X, yes, nominally 5, so it'd be 6. So well, I don't really need to assert that because I just said it. Let's just do this. I am a bit tired this evening. I'm going to set up my initial conditions the way I like them. B, C, D, E, H, L. DCX I'm going to derive from INX. Something was running for a long time. Okay. So INX looks like this now, because I have incremented SP twice. AAFE, AAFF, AB00. We can see the last T state here. We're perfectly aligned. Everything looks good. Let's just wipe the I-8080 ALU star x.png. There. Did I set my mouse cursor up to be able to grab that? I don't think I did. No. So 4 instructions. BC, it's FEAA, FF, AFF, AB00. That looks good. Whoops. Okay, so and there we go. There's all 4 of our INX instructions working. So BC, hold on. Oh, right. SP incremented here, BC incremented here, DE incremented here, HL incremented here. So that is all the increments. And I think I can get the decks done before I fall asleep at the keyboard. In this case, the initial values that I want are AB00, actually it was AB01. So the changes I want to make are search for AA. Oops. Those comments are going to be all wrong, aren't they? Yep, let's regenerate these once we get this edited. BC from AB01 to AB00. There's the first DCX test, which passes. And now we take this, we go down like that. Should be 8 instructions. Okay, AB01, AB00, 010, AB010, AFF, 0100, AFF. Okay, that's all correct, and it's tested. So we have increment register, decrement register, increment register pair, and decrement register pair. I will take that as a win for the night, and I will get this, add a few comments here and there, and get this pushed up to GitHub probably tomorrow. I think that's it for me. So until we meet again, it's I'll keep it small,